Solutions for quiz 0. This is quiz 0, problem 1. Write the closed interval 0 to 1 in set notation. So when we think about an interval, of course, the first thing that goes through my mind is the number line, the real number line. Everything from negative infinity up to infinity. And so then I just kind of ask myself, okay, where is that guy on the line? And I guess I'm just going to go ahead and put 0 right here. And I say, okay, where's 1? It's over to the right. It's right here. 1. And the closed brackets, or the hard brackets, means that we are including those endpoints right there. Okay, so now we have a visual to go along with, right? A visual to have in our head. And what we're saying is, okay, we need to then write a set. And the way that we've been doing this is we say the set of x such that, and if it's not specified, we're assuming that x are real numbers. And so we're saying the set of all real numbers x such that what? Well, we're imagining that we're taking any number from here, x. What properties does it have? Well, it's between 0 and 1. We're going to see that pretty much anytime we do set notation with an interval. That x is going to sit between two numbers, and they're right here, 0 and 1. And it's always at least going to be something like this, right? Then the question is, do we have less than or greater than, and will it be equal to or not? In this case, because we are including them, that's what the closed brackets mean, that we are including it. And so we'll say, yes, including it, it can equal 0, and it can equal 1. And so then that's exactly what we want to write right here. 0 less than or equal to x, which is less than or equal to 1. And then we close our set. And that is how you express this set of real numbers, which we could visualize as all of these points right in here on the number line. That's how we could express that in set notation. Quiz 0, problem 1, part B. Write this set in interval notation. So this is the set of all values x such that x is between pi and 7.2. And here we have that it could be equal to 7.2. Here it says it has to be strictly greater than pi. So I'm going to go ahead and just imagine, again, the real number line. And we're going to say, okay, let's just put these in two places. There's pi. There's 7.2. And now we're just thinking, okay, we're going to take all the numbers in between here. And I notice that, yes, it can equal 7.2. So if we wanted to show that we're including the point 7.2, we use the hard brackets. And we're excluding pi. It has to be strictly bigger than pi, right? So what do we do for that? Well, we use the soft brackets or the parentheses, whatever you want to call it, to show that no, pi is on the outside of that. We are not including pi. We're taking everything just bigger than pi. And so now, what I love about this notation is now our hard work is done. We know it looks like this. We're going from pi up to 7.2. And there's your answer. This is another way of writing the set of all points from pi, but strictly bigger than pi, all the way up to 7.2 and including 7.2. Part C. The set, we want to write the set of real numbers between -2 and 1, not including endpoints, in both set notation and interval notation. Now, almost every time I'm going to do one of these, I'm going to start with a real number line. We're going to imagine we're going from -infinity up to infinity. And then, okay, so now let's see, all the real numbers between what and what? Well, between -2 and 1, so let's put those on here somewhere. There's -2, there's 1. we're taking all of the ones in between, and we're not including the endpoints. So we want to exclude 1 over here. Okay, so that's the notation we use to show we're not including them, we're excluding them. And we are not including 2, so we're taking everything in between there. And now the hard work is done for us, really. Since we already have that picture there, I'm going to go ahead and do the interval notation first. So right there, that's how we do that. That says all the real numbers strictly bigger than 2, from -2, from -2 up to 1, but not including 1. There's the nice picture right there. 1 is outside, he's not in the set. -2 is outside, he's not in the set. We just got those guys right there. So now for the set notation, we imagine if x is any number in there, maybe this is x, maybe this guy's x. At any rate, they all have this property that they're in between those 2 numbers. So I'm going to go ahead and just start by taking x and saying, okay, everything from, it's bounded by -2 and +1. And since I've written it in the correct order, I really don't need to use my brain there. It's always going to have that like that. The only question is, do I make it less than or equal to, or greater than or equal to? Well, since we're excluding them, right, it says not including the endpoints, we can't actually equal 1 or -2, so we just leave it like that. Okay, now I've translated that picture and that interval into an inequality. And I could say, all right, well, now we're pretty much done. We're saying take the set of all x such that x itself is strictly bigger than 2 and less than 1. That's exactly what that is. Quiz 0, problem 2, part A. Write the open interval 0 to infinity in set notation. I love starting off with a picture. The picture's going to be of the real number line going from -infinity up to infinity. Now, okay, looking at the interval, and if these were just regular old numbers, I would say, okay, I'm going to just draw that number right here, and then I would draw whatever that number is over here, but oh, it's infinity. It's past all of that, right? So I'm not going to worry about that. I'm just going to say, okay, now, here's the thing. That's the left-hand side of the set. Are we including 0 or are we excluding 0? Well, the parentheses means we exclude it, and so we're going to do like that. And then say, well, it's everything, well, everything bigger than that. So it's like all of these guys, forever and ever. Okay, so now, to put this in set notation, we need an interval. We need some kind of inequality involving x. And so we say, okay, well, if x is any number that's in there, what properties does it have? Well, it's bounded. It's between these guys, right? So that's usually how we think about it. We say, all right, the thing on the left-hand side of x is this, the thing on the right-hand side is this, right? Now, we could say, do we use the equals? Well, no, we're excluding 0, so x can never equal 0. It has to be strictly bigger. We can never have it equal to infinity, so that's not even a question. But now when we go to put this in a set, by convention, we usually, at least at this point in math, we're not going to worry about specifying that that's the case. We're usually just going to leave that right out because it's understood that, yeah, the stuff we're working with will never get to infinity. So, just by convention, if you wanted to put that in, that's fine, whatever. But usually we just leave it out. We're going to say, okay, it's the set of x values such that 0 is strictly less than x. Or we could say that x is strictly bigger than 0. And we could see, yeah, that is exactly that interval right there. Take any number that's out here, I don't care how big, it has this property. Now another thing, I just want to mention this. if you would have written something like this, x such that x is bigger than 0, and you wrote it in that way, that's perfectly fine too. That it means the exact same thing, right? X is strictly greater than 0, x is strictly greater than 0, or we can say, I guess, 0 is strictly less than x, or whatever. It means exactly the same thing. You should be able to see that pretty easily. This is just me personally, what I like to do whenever I'm writing inequalities is I always like to put the thing that's less on the left-hand side and have it going from the smaller to the bigger thing, because it kind of helps me with this kind of picture I have of the real number line. The less stuff is always over there, and the bigger stuff is always over here. And so then I don't know, it takes some of the guesswork out, you know, when you're putting all this stuff together. But that's just a personal preference. If you wanted to do it like this, that's fine too. Okay, problem 2, part B. Write the set of x such that x is less than some giant number in interval notation. All right, let's see. Again, I'm going to visualize this with the number line. Negative infinities over here, positive infinities over here. We have some big number. Okay, let's just write it down. That's 10 raised to the 10 raised to the 10. Now, x, it says, has to be less than it. X has to show up over there. Okay, so another thing is that it has to be strictly less. So it can't actually equal that number. So our interval is going to have to exclude that number. So we use the parentheses, the soft bracket. And then we're going to say, okay, then x could be all of these guys all the way down to there. Right? Yeah, and you can see, like, there's no lower bound here. This just goes down forever. So when we're thinking about our interval, then the two numbers that we're putting x between is going to be that number. It's not really a number, but that guy and this guy right here. And so we're going from negative infinity up to 10 to the 10 to the 10. And now, okay, we never include infinities, right? So they are excluded. That's going to be an open bracket, soft bracket, however you want to put it, however we want to call it. And now we've already drawn the picture, right? This guy goes like that, and that is that interval. That is the set of all real numbers that are less than, strictly less than, 10 to the 10 to the 10. Problem 2, part C. Write the set of real numbers less than or equal to -7 in both interval and set notations. Okay, so you know what I'm going to start with, the number line. I like to have a picture before I do anything. We're going from negative infinity up to infinity. And now, well, the only number we have here, the only number we're given is -7. So I'm just going to go ahead and throw him on here somewhere. There's -7. And then it says the set of all reals less than or equal to that. Well, that's these guys over here. And so now I'm going to say, okay, do I do the soft bracket or the hard bracket? Well, since it can be or equal to, we are going to take that, like that. That gives us the picture that we're looking for. We're taking all those numbers down, right? It could be anything that's less than. So then, just like in our previous problem, right now we have these guys. We're going from negative infinity up to -7. We never include infinities, so that's always soft. We are including -7, and so that guy's hard. Now, we want to turn that into an inequality involving x so that we could write it in set notation. So we're going to say, well, if x is any number in that set, it is between those two values. So x is between negative infinity and -7. We could say, okay, now, all right, the infinity thing we don't need to worry about. We're not even going to write it. But this guy now, we are including it, so I am going to write it like that. And like I just said and said before, we usually don't bother writing that in our set notation, at least not yet. So to make that a set, we're going to say, okay, the set of x such that x is less than or equal to -7. And so there we go. That set of real numbers is exactly the same as that set of real numbers, which looks like that on the real number line. And that's it for problem 2. Quiz 0, problem 3, part A. Write the interval -infinity up to 0 union the open interval 0 up to infinity in set notation. You could guess what we're going to do first. That's right. Okay, so going from -infinity up to infinity, let's start with this guy right there. Goes from -infinity, goes all the way up to 0. Go ahead and put a 0 right there. And you can see we are not including 0. He stays out. Now the second interval starts at 0 but doesn't include 0, so we have this thing right there and then goes all the way up. Okay, so it looks like we are going to need 2 inequalities because we have 2, this is called disjoint sets. These are sets that are actually separated. So, okay, let's see. Same way we always do. We have that symbol and that symbol, and x goes between those symbols. Clearly we have that. The only question is, do we put the equals or not? We never do with that. In this case, it is not included, so we don't make it equal. Now for this part, we got that and that, so we're going to go from, we're going to say x is between, oops, this is what goes on in my head. X is between 0 and infinity, and so it looks like that. Then the question is, do we make them equals or not? And no, because we're not including 0, so we're not going to make that equal. Excuse me, we never do it with infinity. And again, we could forget about the infinities. So now we have it. Question is, we're going to go specify this inside a set. Do we say this and this are true? Or do we say it's this or that are true? Well, again, if x has the property that it's down here, it can't also have the property that it's up here. So we're saying either or of them must be true for any one given x. And so we're going to say the set of x such that either x is less than 0 or 0 is less than x. And we're done. Now again, we could have done this a couple different ways. Like I said, we could have had something like that, and it would mean the same thing, but already, like, I don't like this because even as I was writing this, I was like, wait, is that right? Like this, I could imagine it, right? It's like, oh yeah, x is on that side of 0. That's what that says. Oh yeah, x is on this side of 0. That's what that says. But this is like, well, x is less than, yeah, so he's over there. Okay, good. X is, oh, x, yeah. So if you wanted to put that in there, that's fine too. I personally don't like doing it that way. So anyway, there's your answer to part A. Part B, write the set of x such that x is greater than or equal to -2 and less than 1, or x is greater than or equal to 2 in interval notation. Okay, now we have 2 inequalities here. Let's think about this. See where these guys are going to show up. Well, we have 3 numbers that are given. We have -2 and 1. So
negative 2 is here. We'll say 1 is here. And how about positive 2 is right there. And I don't think I mentioned this in the last one, but this or right here, it kind of bothers me at first. When you first hear it, you're like, wait, but shouldn't it be and? Like, were you saying like that it's either this set or it's that set? Like, isn't this one set? I don't know. It just sounds weird to me. We'll talk about that in just a second. So right now, let's just kind of pretend we're not working on that. All we're wondering is, okay, what does that look like? Well, that's the values of x that are between here and here. And so we're starting there, and it looks like we are including minus 2. Minus 2 can be one of the values, so we're including it in our set. We go up to 1, but we are not including 1, so we are going to exclude this guy. Okay, now the next part says that x has to be bigger than 2, but it could be equal to 2. So it looks like 2 is included in the set. And then we're taking everything beyond, all the way up to infinity. Okay, so now let's write this as intervals. We could say if x is in this set, well, x could be here. X could be over here. X could be maybe right here, but you'll notice any one x can't be in both of these sets at the same time. You can't have a number that is simultaneously between negative 2 and 1, and at the same time between 2 and infinity. Like, you could have different ones that do, yes, this x satisfies that, this x satisfies that, but there's no one x that works for both of them. So that's kind of what the or means right there. We're saying any one x that you choose is either in that set or it's in that set, and we're considering these two things as one set. So it could be a little confusing, but that's why we use or and not and in there. Okay, moving on. This guy then, in interval notation, we've already drawn the picture. It's going to look like this. From negative 2 up to 1, not including the 1, but including the negative 2. Union with 2 to infinity. Again, I'm just really copying the picture that I've already drawn on the number line. We are including 2 and we're taking everything out to infinity, but we are not including infinity just because we never do. Infinity is not a number. So there you go. Again, this is kind of like saying any one x is either in this set or it's in this set. But we're using union to say that this is kind of, we're considering these as one set. In fact, if you are taking logic or something like that, they will actually call this symbol or. It's the same thing in certain circumstances. So, okay, that's how you write that in interval notation. Part C. Now this is a tricky one. This is, we want to write the set of all real numbers greater than negative 2, less than or equal to 1.2, and not including any integers. And I wrote a hint on there that said to draw it out or write it out, and then think about picking out or pulling out the integers. So we're gonna just kind of forget about the integer part right now and think, okay, what would this interval look like? And we want to do this in interval notation and set notation. I think it's so much easier to start with the interval notation. In fact, I even start with drawing a picture. I'm going to say from negative infinity up to infinity. And let's see. They have to be greater than negative 2. Okay, so that's as far left as we're going. Here's negative 2. Less than or equal to 1.2. So 1.2 is the highest that they'll ever get. bracket. Okay. Now, let's forget about the last part there and just say, all right, set of real numbers greater than -2. So we have to exclude -2. It doesn't say anything about greater than or equal to. It has to be strictly greater. So we're going to say, okay, this has to be a soft bracket, parentheses. Okay. Now coming all the way up, it says it has to be less than or equal to 1.2, so we can include 1.2. So we'll go ahead and do it that way. Okay, now what about this not including any integers business? Well, let's just think about where the integers are on here. -2 is an integer, but he's already outside the set, so we're not going to worry about him. Moving our way up, the next integer would be -1. The next integer would be 0. And then the next integer would be +1. Okay, now, so if we had this set right here, and we wanted to pick out one of the integers, basically what I'm saying is we're just going to exclude them, right? When we excluded -2, we drew something like this. So right now I'm just kind of thinking with the pictures, right? Just thinking symbolically here. Like, what would that look like? Well, if we're taking everything from here up to here, but we have to exclude him, we'd have to do something like that. That would be excluding -1. But we're not done, right? I mean, we don't want to then just say, oh, that's it, that's all. Well, no, we have to keep all of this. We're just pulling these guys out. So what would this look like? We have to keep all of these guys, but we want to exclude -1, so it would look like this. Moving our way up, keeping everything in here, but excluding 0 would look like that. Then past 0, keeping 0 out, but keeping all of this stuff, we'd say, well, we would do something like that. Moving our way up to 1, doing that. And on the other side of 1, doing that right there. Now, okay, so right now all we've done is just kind of made pictures, right? Now let's translate this into interval notation. And we could say, all right, well, here's my first interval. It's going to look like this. And it goes from there to there, right? So we're taking all the numbers between -2 and -1, but not actually including the integers themselves. Okay, we're going to union that with another interval that looks like this. Another interval with soft brackets, going from -1 up to 0. From -1 up to 0. So all the numbers between -1 and 0, but not including -1 and not including 0. Union that with the next one, it looks like this right there. And it goes from 0 up to 1, so from 0 up to 1, not including 0, not including 1. Now the final one, we'll union that with our final interval, and it looks like this. We got that and that right there. So we've already done the hard work by drawing it on the line. Now I'm just copying down what I see. Okay, so it goes from 1 up to 1.2, and it includes 1.2, which it says it can less than or equal to 1.2, so we're good to go. So that is that set in interval notation. Now if we wanted to do this in set notation, we're going to need inequalities involving x. And it looks like we're going to need 4 of them, right? And so, again, kind of mindless work right here. We're going to say, well, x has to be between these two numbers. What does that look like? Well, the one on the left does that. X is between that and that right there. Then I ask, can they be equal on either of them? No, that's soft brackets. That means no equality. Okay. Union means or, when we're writing in English. Or it could be the case that it is between -1 and 0. Okay. That takes care of that. No equalities there because we are strict, right? We're strictly greater than -1 and strictly less than 0. Or it could be the case that x lives somewhere in here. X is between 0 and 1, not including either of them. Or it's the case that x is between 1 and 1.2. And now I have to use my brain and say, well, wait a second. That means that it could equal 1.2, so I have to do that. Make it x is less than or equal to 1.2. And now I've described the set, right? Any given x that lives in this set lives in one of these guys right there. He either lives in here, or he lives in here, or and so on, right? So we are done. That is the description of the set, and we're saying that it is the set of all x such that it's either the case he lives in there, or there, or there, or there. That was a hard one. Quiz 0, problem 4, part A. Write the set of x such that the absolute value of x minus 1 is less than or equal to 0.1. Now, in the quiz itself, I worked out an example where it was strictly less than. And you're going to see we're going to end up doing the exact same thing. The only difference is we're going to have a little equals under that one. But let's just go over it, right? We're thinking, okay, that is some set of numbers. And if I could get x by itself as an interval, then I could write it in interval notation, right? That's the idea. We're saying, here's a set of x, and it has some properties. It's between something. If we could just find out what the lower bound for x and the upper bound for x, then I could write this as some kind of interval. So in order to do that, I'm going to start by just saying, okay, well, let's look at what this thing means. Now, this is where the bread and the butter of the set is. It's like right here. All the information about the set is in that inequality. So we're going to say, okay, what does that mean? And don't think about it too hard because, yeah, like you could go off the deep end really quick. We're just going to say, wait a second. We know that there's a trick with this type of thing. When you have an absolute value less than some number, that's the same thing as saying that whatever's in there is bounded between this and negative whatever it is, right? So whatever is in there, all it happens to be x minus 1, it's bounded between those two values. Okay, now the whole point was get x by itself, right? If we could get that x alone and find out it's just x is between this number and that number, then we'd have an interval and we could write it as interval notation. So what I'm going to do is say, okay, how about plus 1, and plus 1, right? X minus 1, to get rid of the minus, we go plus 1. That leaves me, well, let's go over on the far left-hand side. So that's the same as 1 minus 0.1, which should be 0.9. Okay, now let's see. That gives us, well, the whole reason I did that was to get x by himself, right? So the negative 1 and the plus 1 cancel. We're just left with x. Now over here, 1 plus that or that plus 1, doesn't matter. We end up getting 1.1. So 1.1. Let's think about where that guy lives. We don't necessarily need to do this if you don't feel it's necessary, but I like to do it. We're going to visualize this guy. Okay, we're going from 0.9 up to 1.1. We are including that because of the equals. We're including that because of the equals. And so now there's your interval. That's what it looks like. It has that shape. It goes from 0.9 all the way up to 1.1. There it is. Part B. Write the set of x such that the absolute value of 2x minus 1 is strictly less than 2. Write that in interval notation. Okay, now, this is where all the information is. If we could rearrange this to get an interval in order to get bounds on the value of x, and we'll have an interval. And so I'm going to just start off by saying, okay, let's look at this thing. What does this mean? Well, that means that the magnitude of that number right there is less than 2. Okay, well that means that it's bounded by 2 and negative 2. Right? So now it's a matter of just getting x by itself. And right now it's just kind of like solving an equation, right? I'm looking at x, I need to get x by itself, but by the order of operations, x first gets multiplied by 2, then it gets 1 subtracted from it. So it's kind of like if you put on your socks, then you put on your shoes. To get back to normal, right, to get back to a bare foot, you have to take off your shoes, then take off your socks. So the first thing that happens is multiply by 2, then subtract 1. It's the last thing that happens. That's like putting on the shoes. So we have to take off the shoe. In other words, we need to get rid of the minus 1 first. Then we could get to the other thing. So I'm going to get rid of minus 1 by doing the opposite of minus 1, which is plus 1. But I gotta do that to everybody here. So I'm gonna do that all the way across. Okay, now that gives me minus 2 plus 1 is minus 1. Strictly less than 2x, because that was the whole reason I did that, was to get rid of that 1. Okay, 2 plus 1 is 3. Now, okay, now it's just the socks. Now we only have our socks on and we need to take them off. Well, x times 2, what's the opposite of times? How do you undo times something? Well, you divide, right? We get rid of the 2 by dividing by 2. So x got multiplied by 2. To get rid of that, we go divide by 2. We got to do that to everybody. So we do it across the board. Now we have negative 1/2 less than x less than 3/2. Right there. Okay, well there's our interval. Now let's, in order to get this into interval notation, I like to just real quick, I'm going to draw a line and say, okay, we're going from negative 1/2 all the way up to 3/2. And we are not including those endpoints. We are going to exclude negative 1/2. We are going to exclude 3/2. And so finally, minus 1/2 up to 3/2 is our interval. Now, let's just take a second and check this, right? Because like we kind of went off into the deep end. We used some crazy stuff to turn this into this. Let's just make sure that it works, right? I say that if you take any number in that interval, it will have that property. Let's check a couple. We have in this interval, we have the number 0. So let's plug 0 into this right here and see if it's true. I'm going to go ahead and erase this. This is the final answer for part B. All right, I'm erasing that. Now we're just checking to see, like, does this make sense? Okay, well, if we have 2x minus 1, and I were to plug in a 0 for x, I would have 2 times 0 minus 1, which is the same thing as 0 minus 1, which is just minus 1. The absolute value of minus 1 is 1. Is that less than 2? Yes, indeed, it is less than 2. So, all right, at least that part's good. What's another number in there? How about the number 1? Let's check that and see if it works. All right, 2x minus 1. We're asking, is that indeed less than 2 when we plug in a 1? Let's see. 2 times 1 minus 1 is equal to 2 minus 1. Which is equal to 1. Absolute value of 1 is 1, which is indeed less than 2. Check. Okay. Now, here's the thing. I want to kind of go into this for just a second. Let's say you have something really complicated here, and you've done a bunch of crazy calculations, and in the end, you end up with an interval, and you're like, I don't even know if that makes sense, right? Like here, I feel pretty confident about this because we didn't really need to do any real work. But one thing we could do is check to see the endpoints, right? Like when I plugged in these middle points here, I plugged in 0 and I plugged in 1, and they were obviously true. Well, what we could do is say, well, what happens when you just go outside of that interval, right? So like for instance, what happens if I plug in something that's just outside? That should cause this inequality to just be false. Let's check it. Let's see what happens when we plug in 3 halves into this interval. We have 2x minus 1. I'm going to plug in 3 halves, and we get 2 times 3 halves minus 1, an absolute value. Now, one thing you can notice is that the 2's cancel. You have a 2 divided by a 2, 2 in the numerator, 2 in the denominator. They're gone, leaving me with just a 3, right? Minus 1. 3 minus 1 is 2. The absolute value of 2 is 2. And that, it just doesn't make it. It's just not true, right? If you had the equal to, it would work, but then, so we could see, just going outside of the interval just breaks the inequality. That's a good sign. It's a good sign that you did things right and that, you're on the right track. You could feel pretty confident about this. But if you're still unsure, right, you're like, well, I don't know. We did like 40 lines of work here and everything got really hairy. Well, maybe we could check the other one too. So let's check the other end and see if it just breaks the inequality. So if we are in this interval and we go just outside of it, we'll be at negative 1/2. So let's plug that guy in. 2. Now, when x is equal to negative 1/2, that's what that looks like. We could say, okay, the same kind of trick. 2 divided by 2 goes away, and you're left with negative 1. That just reduces to a negative 1, minus 1. Minus 1 minus 1 is negative 2. The absolute value of negative 2 is 2, and it just breaks the inequality. It's not technically less than itself, so no, that doesn't work. So, long story short, if you've been working on an inequality and a bunch of crazy stuff happens and you're really not sure about it, you don't know what to do, check the endpoints, and you might feel a bit more confident that, okay, this seems right here. Problem 4, part C. Write the set of x such that the absolute value of 1 minus 2x is less than 2. It's a very similar problem here. Let's just go ahead, plug along like we've been doing. We know we need an interval in terms of x. And so to get an interval, I'm going to start with the information here. 1 minus 2x strictly less than 2. Okay, so that means the same thing as it is bounded above and below by 2 and negative 2. So whatever's in there is bounded. Okay, now, kind of like we did before, right? It's like, well, wait, what am I going to do first? Well, let's look at x. We're trying to get x by himself. First thing that happens for order of operations is he gets multiplied by a number. Then he gets a number added to him. You could think about it that way, right? Like 1 minus 2x is the same thing as negative 2x plus 1, right? And just so the last thing that happens to x is plus 1. So let's get rid of the 1 first. We're going to say plus 1, the opposite of plus 1 is minus 1. So minus 1 from every side. Minus 2 minus 1 is minus 3. 2 minus 1 is 1. Now, okay, we have an x multiplied by negative 2. How do we undo multiply? Well, we divide. So we're going to divide by negative 2. But, when I multiply or divide an inequality by a negative number, it flips the sign, right? So this is my little notation for that. I like to just do this to say, okay, this is not official notation, but I like to do it so I keep myself honest and make sure that I haven't forgot that. Okay, so we flip the signs. Now let's see what happens. Well, the whole reason I chose negative 2 in the first place was to get that to cancel out, get x by himself. Negative 3 divided by negative 2 is positive 3 halves. Okay. 1 divided by negative 2 is negative 1 half. Now, I don't like writing stuff like this. I don't like big stuff over there and small stuff over here. So this is just me personally. I'm going to rewrite it to go in ascending order. I'm going to put the smallest thing on the far left side, so minus 1 half. And then, yeah, it should open towards the x, right? Like, that's the smaller thing, comes up to the x. Then the point goes to the x, and so it goes to the bigger thing, 3 halves. And we could see, like, yeah, that means exactly the same thing. I just like to write it that way, so now I have a visual, and I could say, oh, okay. It goes from minus 1 half up 3 halves. And, okay, no equalities, right? There's strictly, right? This is all strict, so we are not going to include these endpoints. Finally, the interval we're looking for, we've already drawn it, minus 1 half up to 3 halves. Huh, it's the same interval as before. Interesting.
Quiz 0, problem 5, part A. Right, the set of x such that the absolute value of x minus 1 is strictly bigger than 0.1. Right, that an interval notation. Okay. Now this is subtly different from the other one. We're saying that a number, whatever happens to be in there, let's just for right now, we'll think about it as just some number, y. Okay, if y, in absolute value, has to be bigger than 0.1, well, where could it possibly live? If here's 0.1, right? Well, if y indeed is positive, then we don't really need to worry about it. If y is a positive number, say 2, if 2 equals y, then he's good. If y equals 1, then he's good. But y, if he's positive, can't live down here. Y can't be like 0.08 or something like that. Because, well, that's kind of obvious when it's the case where that number is a positive number. What if y were a negative number? What if y were, say, negative 2? Would that work? Well, yeah, because, I mean, you put in negative 2 here for y, and you'd say negative 2, the absolute value of negative 2 is positive 2. And it is the case that that is bigger than 0.1, so we're good to go. So what if we started bringing him in this way, right? Like if we're down here at negative 0.1, and he's on that side of it, right? Like, again, I guess negative 1 is a good one. Negative 1. If negative 1 is y, then we could see, yeah, if y is equal to negative 1, then the absolute value is just positive 1, which indeed is bigger than 0.1. Problem's going to happen when you get on this side of it, right? If you were to take your y, if your y value were, say, I don't know, negative 0.01, right? Let's just see what happens. If y is equal to negative 0.01,
which is not less, or I'm sorry, which is not greater than 0.1. It would not work. There's kind of this forbidden zone going on in here. Ditto at 0, right? If you plugged in a 0 there for y, you'd have the absolute value of 0 is 0, which is certainly not bigger than that, right? So I just kind of think about this as there's this forbidden zone in here. Y could be very, very negative. Y could be negative 100 equals y. If that's the case, if y equals negative 100, we'll just do this, right? The absolute value of negative 100 would be positive 100, which indeed is bigger than 0.1. So we could take all of those values, all of these values, there's just this forbidden zone that's bound by the positive amount of that, 0.1, and the negative amount of that, negative 0.1. So that's where we get that nifty little formula or theorem, I guess, that I wrote in Quiz 0, Part 2. I think it shows up in 2. So from that, I wrote that this thing means the same thing as it has to be bigger. When it's positive, it has to be bigger than it. If it's negative, it has to be less than the negative value of whatever that thing is. Right? So that's what we were saying. If y happens to be positive, he's got to be up here out of the danger zone. If he's negative, well, he has to be way down there out of the danger zone. So that's where all this comes from. And so now we could see, well, yeah, this is what I was saying about any expression that goes in there is, this is true. So that expression, it's not y, it's actually x minus 1. And so I'm just going to say, oh, okay, well, there's that x minus 1 has to go right here. X minus 1 has to go right here. Now we have our two inequalities that we're going to work with to get an interval for x. Or it's actually going to be two intervals for x. So over here on the far left, I'm going to say, okay, you have x, you subtract off 1. How do you undo subtract 1? Well, you add 1. Do that to both sides. That gives x by himself. X has to be less than 1 minus 0.1 is 0.9. Or it's the case that, okay, we have x minus 1, get rid of the minus 1 with plus 1, do it to both sides. 1.1, strictly less than x, just like that. Now to put that in interval notation, right, we could just think about a number line and say, okay, here's 0.9. Here's 1.1. X has to be on that side of it, not including it, so he's got to exclude. It can't be equal. So x could be any one of those guys. X has to be strictly bigger than that guy, and so we do this. It could be any of these guys, all the way up to positive infinity. So there are your intervals, right? From negative infinity up to there, up to 0.9, not including 0.9, union, right? Or it could be the case that it's in here. It could be that it is 1.1, not including 1.1, up to infinity, not including infinity. All right, and there is the answer to part A. All right, part B. We are to write the set of all x such that the absolute value of 2x minus 1 is strictly bigger than 2. Okay, again, we need an interval or a set of intervals that describes this, or that this describes. The information is right here. 2 minus 2x minus 1 in absolute value. And we say, well, if we could just get x by itself, then we could have some kind of interval. We could find our bounds for x, right? The problem is, what does that mean? And so we're going to refer to our quiz and say, yeah, that's right. That means that it's either the case that 2x minus 1 is a positive number, in which case it'll have to be bigger than 2, or that right there is a negative number, and so it would have to be less than negative 2. Okay. Now, we have to get x by itself. So there's the same expression on either side, so I'm just thinking, okay, x gets multiplied by 2, then he gets subtracted by 1, so the last thing is subtract 1, so I'm going to add 1 to get rid of that. Plus 1 over there, plus 1 right here, leaving me with 2x, which is the whole point, getting x by himself. Okay, negative 2 plus 1 is negative 1. I'm going to do the same thing over here right now because, hey, I don't really have to use my brain. I just do the same thing that I just did. 2 plus 1 is 3. Okay, now 2x. Okay, so now I'm thinking, okay, getting x by itself. X gets multiplied by 2, so to get rid of that 2, I got to divide by 2. I'll do that over here. I'll do that right there. Cancels out. Gives me that guy right there. X is less than negative 1/2. Over here, same kind of thing. To get rid of the multiply by 2, we divide by 2. So I do that. The whole reason to do that was to get x by himself. That's where it is there. On the other side, we have 3/2. Okay, so now thinking about a number line. I'm going to say, all right, two numbers we're working with is negative 1/2 and 3/2. Okay, so there's 3/2. Now x has to be on that side of negative 1/2, and he cannot equal negative 1/2. So he's going to have to do that right there, all the way down to negative infinity. On the other hand, we have 3/2. X has to be bigger than 3/2. It cannot equal 3/2, and so we're going to do that right there. But it can be anything bigger than it, so it goes all the way up to infinity. There are my intervals. Now I just need to write them out. Minus infinity up to negative 1/2, not including it. Union that with 3/2 up to infinity, not including infinity. Now, okay, this is like in the last problem we worked on, one of those cases where it's like, wait a minute, hold up. Are we sure about this? Like, let's just make sure that this works. We'll do a couple of these. I'm going to go ahead and erase the work we did, but keep the final answer. This is your final answer, right? This is the interval notation for that set. Let's just double check. So, okay, let's suppose that we're somewhere over here. 3/2 is 1.5, so 2 is a perfectly good one. That lives in there, and let's just see what happens when I plug in 2. 2x minus 1, so when x is equal to 2, we get 2 times 2 is 4, minus 1, okay, 4 minus 1 is 3, absolute value of 3 is 3, and indeed that is bigger than 2, okay, so I'm feeling a little bit better about what we've done. Let's just check something over here. How about a minus 1? Minus 1 is certainly on that side of minus 1/2. He is in that interval. So let's just see what happens when we do that. When we plug in a minus 1 for x. 2x minus 1, but we're plugging in a minus 1 here. Okay, 2x minus 1. I'm sorry, 2 times negative 1 is negative 2. Minus 1, is negative 3. Hey, what do you know? Negative 3, absolute value is 3. And that is indeed bigger than 2, so that checks out. Okay, now you see what I mean? Like, it's kind of weird when you say, what if this value is positive? Well, okay, and what if this value is negative? And it's like, well, it's an expression. What does that mean for x? You know, you're saying that, it could be kind of confusing, but now we're kind of seeing what you mean. If your value's over here, like in this case, negative 1 is in this part of it, then it is indeed the case that this entire thing, when you evaluate it out, it does end up being negative, right? So, all right. One final thing, I really want to drive this point home. Again, we did a lot of crazy stuff, and I want to make sure I didn't do anything wrong, so I'm going to check the limiting cases. I'm going to try to break this thing and say, if I take a point that's just outside of this interval, in particular, if I take the point negative 1/2, it should just break that inequality. Let's see if it does. 2x minus 1, only instead of x, I'm going to write minus 1/2 and see what happens. Okay, the 2's cancel, or rather 2 divided by 2 is 1, leaves me with a negative 1 minus 1. Negative 1 minus 1 is minus 2. Absolute value of minus 2 is 2, and it just breaks that inequality, right? Ditto with 3/2. If you plug in 3/2 there, you'll see that it is just going to break it. And so I feel pretty good about our final answer. I'm going to go ahead and say, yeah, I think we're good to go with that. Problem 5, part C. Write the set of x such that the absolute value of 1 minus 2x is is greater than or equal to 2. Write that in interval notation. Okay, let's use this, which defines the set, to get an inequality, to get bounds on x. Okay. This means that that number, if positive, is bigger than or equal to 2, so 1 minus 2x is bigger than or equal to it. Or if it's negative, then it has to be less than the negative of whatever that number is. So I write it as negative and say, okay, like that. And then I throw everything over here. Minus 2x. Okay, let's start over here. I need to get x by itself. So I'm going to say, okay, x gets multiplied by 2, and then when he gets multiplied by a negative 2, then he gets a 1 added to him. The 1 is the last thing that happens to x, so let's start there. I'm going to subtract 1 there. The 1 minus the 1 is gone. I have minus 2x is less than or equal to minus 2 minus 1 is minus 3. Or it's the case that same exact reasoning. We have to say minus 1 from both of these. 2 minus 1 is 1, less than or equal to negative 2x. Okay, now x gets multiplied by negative 2. We need to get rid of that, so we're going to divide by negative 2. But when we divide by a negative number, we have to flip the inequality. So we get x. Now we write it backwards. X is greater than or equal to 3/2. Because negative 3 divided by negative 2 is positive 3/2. Okay, same thing over here. Multiply by negative 2, we undo that by dividing by negative 2. Do that to both sides. Uh-oh, better flip that inequality. So I'm going to do that first so I don't forget. Now, okay, the x is all by himself, finally. That's what we're looking for. And then over there we have 1 divided by negative 2 is negative 1/2. I hate writing it this way, so I'm going to say, wait, what's the smallest thing? The smallest thing here is x. Let's write him over there. Gets bigger, okay, so it goes over here and goes up to minus 1/2. Didn't write my or. Go. Now, okay, then as we keep getting bigger and bigger, we're going to get to 3/2. And then we get bigger and bigger and get to x finally. Okay. Now this is the way I like it. I could say, here's my number line. We have two numbers. We have negative 1/2 over here. We have positive 3/2 over here. Now x has to be on that side of it, and so the negative 1/2, but ooh, look, we can include it. So we're gonna say, okay, inclusive and everything that's less. That goes all the way down to negative infinity. Cool. Now what about over here? Well, x is on this side of it, and we can include 3/2. So we're gonna say include 3/2. Take everything that's bigger all the way up to positive infinity. So that interval we write from negative infinity up to minus 1/2. We never include infinities. In this case, we are including negative 1/2. We're going to union that with the other interval, which goes from 3/2 up to infinity. We are including 3/2, so I'm going to put the hard bracket. And we are excluding infinity always, and so we use the soft bracket. So that looks like it. That is that set written in interval notation.